Hi, my name is Mohammad Delpasan. I'm a Master of Applied Science student at Concordia University. I'm going to present you our work, Damage Detection Procedure using the Spectral Element Method. It is a part of my thesis under supervision of Dr. Erkman from the Building, Civil and Environmental Engineering Department and Dr. Gannison from the Mechanical, Industrial and Aerospace Engineering Department. In this presentation, I'm going to talk about the motivation behind the spectral finite element method, and we will see how we can apply it to solve the problem of vibration of Euler-Bernoulli beam elements, and we will see how the result from the spectral analysis is incomplete and how we can build the transient response based on that. We will also see how we can extract the natural frequencies using the dynamic stiffness matrix that we get from a spectral finite element formulation, and we will see the result of a damage detection tool that we developed using our spectral analysis tool. Dynamic analysis is an important area of research when it comes to damage detection. For example, impact hammer testing is often used to locate the lamination in laminated composites. But the lamination only reveals itself in the higher modes of vibration. So on the screen here we have the results from a study in 1988 on the effect of mid-plane delamination on natural frequencies of laminated composites, and as you can see, the delamination has affected the higher modes of vibration much more significantly than the lower ones. The graphs here on the screen shows the dependency of the conventional finite element method on the number of elements. So the horizontal axis shows the number of elements in the model, and the vertical axis shows the frequency that was captured by that model. And as you can see, as we increase the number of elements in our model, we get closer to the analytical solution. And then another interesting fact is that we get a much higher error when we try to capture higher modes of vibration. In order to resolve this issue, we can replace our model with a spectral finite element model. So on equation 2, we have the dynamic differential equation of motion of the Euler-Bernoulli beam element, and we can see that the element has 2 degrees of freedom at each point, 1 transverse displacement and 1 rotation, and rotation is the derivative of transverse displacement, so we basically have 1 independent variable, which is w. W is a function of x and t, but we can replace it with its Fourier transform in the frequency domain and insert it back into equation 2, and that gives us equation 4, that is the function of x and omega. And if we try to solve equation 4, we will see that it will have a form as in equation 5 with g1 and g3 interpolating the transverse displacement inside the element, and there are exact shape functions, and g2 and g4 do the same thing for rotation. Using the exact shape functions derived in the previous slide, we can find the vector of nodal degrees of freedom and the vector of nodal forces for our element, and we can relate them together using the dynamic stiffness matrix. Now that we have our dynamic stiffness matrix, we can find the response of our structure under any excitation functions. So our excitation function is a function of time, and if we take the Fourier transform of that, we will have our excitation function in the frequency domain. And we can use the dynamic stiffness matrix to find the response of our structure in the frequency domain, and then use the inverse Fourier transform to bring the results back from the frequency domain to time domain. In order to investigate the performance of our spectral finite element model, 2 case studies are done. A simply supported beam is modeled with 2 spectral elements, and a concentrated load is applied in the middle, and we're interested in finding the transverse displacement of the middle point. So a step load and a sine load is applied in the middle, and as you can see, the response under the step load is a step load, and the response under the sine load has a sine shape, and they match very closely with the analytical solution. The results that we get from a spectral finite element method is only in the frequency of the excitation, but when we look at the response of undamped single degree of freedom system under harmonic load, we'll see that the response has three terms. One term is in the frequency of excitation. The second term is in the frequency of the structure and depends on the initial conditions of vibration. And the third term is also in the frequency of the structure but does not depend on the initial conditions. We can also write the response using the Duhamel's integral, and that response has two terms. One is in the frequency of the structure and depends on the initial conditions of vibration, and the second term is the Duhamel's integral itself. So if we compare the equations 9 and 10 from the previous slide, we'll see that the Duhamel's integral is equal to the part of the response that is in the frequency of the structure but does not depend on the initial condition, plus the part of the response that is in the frequency of the excitation. We can also rewrite the Duhamel's integral itself as an integral from 0 to infinity minus an integral from t to infinity. And if we apply that into equation 12, we'll see that the part of the response that is captured by the spectral finite element method is equal to the integral from 0 until infinity, and the integral from t to infinity that is in the frequency of the structure is not captured by the spectral finite element method. There is a method in the literature that suggests that we can build the transient response if we have the steady state response that we get from the spectral finite element, and if we have the initial conditions of vibration, which we do. So it suggests that the transient response can be represented as a corrective function that is equivalent to the difference in the total response minus the steady state response. And the corrective function itself can be represented based on its initial values. So because we have access to the steady state and the initial conditions of vibration, we have access to the initial conditions for the corrective function, and thus we can build the transient response. The method can be extended to multi-degree of freedom systems as well. If we have access to natural frequencies of vibration and their corresponding modes of vibration and the mass matrix of the system, we can add the transient response as a superposition of contribution of different modes of vibration. In order to find the natural frequencies of the system, we need to find an eigenvalue problem. In the case of ordinary finite element method, we would have to solve a linear eigenvalue problem. But in the spectral finite element, because of the nonlinear terms on the dynamic stiffness matrix, we would have to solve a transcendental eigenvalue problem. The Wittrick-Williams method is a robust algorithm to find the natural frequencies of a system if we have access to its dynamic stiffness matrix. The method depends on Rayleigh's theory of sound, which says if a constraint is imposed on a structure, the number of its natural frequencies which are less than a certain threshold, let's call that omega star, will increase only by 1 or 0. The algorithm suggests that you can find the number of natural frequencies exceeded by a certain value, like omega star, by calculating J0, which is the number of natural frequencies of the totally constrained structure exceeded by a certain value, plus the number of negative values on the diagonal of the upper triangularized stiffness matrix of your system. And then you can use bisection method or any other root finding methods to search for the natural frequencies that are in a certain range. A case study is done to see how accurately we can find the natural frequencies of the system using the Wittrick-Williams method. And as you can see on the column on the right, the results from using only 2 spectral elements give us very close values to the analytical solution, while even with using 10 elements with ordinary finite element method, you will still have errors in your result. Now that we have access to the natural frequencies, we can extract the mode shapes of the system based on that, and calculate the transient response using the method I talked about previously. So again, we put a concentrated force and the sign load in the middle of our simply supported beam, and use a lumped mass matrix and use only the first mode of vibration to see the results, and we see that the results match very closely with the analytical solutions. We can introduce damage to our model by inserting an element with a reduced modulus of elasticity with a certain length at a certain location. We can move the element along the length of the beam and change its properties until the dynamic characteristics of our model matches the dynamic characteristics of a measurement test on a real structure. The cost function is a metric that takes in the dynamic properties of the trial structure and the real structure, and its output is an indication of how close the model is to the real structure. So the problem that we'll try to solve is an optimization problem that we try to minimize the cost function by trying different structures. Genetics algorithm is adopted to take care of the optimization process. Each trial structure has a signature that shows the location and the length and the amount of reduction in the damaged element. The first population is generated randomly within the constraints of the problem, and the fitness of each member of the first population is calculated using the cost function. The next generation of our solutions is created based on the previous generation through three procedures, which are pair selection, crossover, and mutation. The generations are created until we pass a certain threshold, and then the algorithm stops. The algorithm was used to update the model of a simply supported beam using its first three modes of vibration, and by only looking at 2.37% of all the possible cases, the genetics algorithm updated the model. We are hoping to use a spectral element method to model laminated composites and extend our damage detection algorithm to find delamination in laminated composites. And also we are hoping to build a damage detection algorithm with a data-driven approach to consider modeling error when we are dealing with vibration measurement data. Here's the list of the references that we used in our research, and thank you very much for your attention.